Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're going to be covering systems of linear equations and how matrices give us a clean way to package an entire system as a single statement. We're following Ruth, a PhD student who's working on her dissertation, trying to build out her matrix-based methodology to get her dissertation done. Today she's working on how a multi-equation portfolio problem can get compressed into a single matrix expression. She turns back to her dissertation chapter. So we've defined the basic notation of matrices, how they work, what the vectors are, and what the entries mean. But so far, all we've done with matrices is use them to organize different sets of data. We've organized the returns of different assets into a single rectangular matrix, and we've organized the covariances of stocks into a square matrix. But matrices have applications that extend beyond just the organization of data. For example, one of the most useful ways we can use matrices is to represent systems of linear equations. What exactly does this mean? Well, let's think of a scenario where we have a portfolio that has a certain set of targets that we want to make. In order to hit those targets, we need to define the weights of each of our assets and how they relate to hitting those targets. This set of how each individual asset ends up contributing to each target is what a system of linear equations is designed to represent. Let's start with a simple example. Let's say there are two stocks available, stock A and stock B. Let's suppose we want to construct a portfolio of those two stocks so that we have specific exposure to only two factors. The first factor we're going to call the market factor, beta, and the second factor we're going to call the value factor. The market factor measures how much the portfolio moves with the broad market index, and the value factor measures how much the portfolio tilts towards value stocks. Through analyzing historical data, we can actually figure out how much each of these stocks is exposed to these two factors. We find that stock A has a market exposure of 1.2 and a value exposure of 0.3. Stock B has a market exposure of 0.8 and a value exposure of 0.9. Our portfolio has a target in mind. We want to have the portfolio's overall market exposure be equal to 1, and we want the portfolio's overall value exposure to be equal to 0.5. Our portfolio is described by two weights, and we'll call them W sub A and W sub B. They are the fraction of the portfolio invested in stock A and the fraction invested in stock B. The portfolio's overall market exposure is the weighted sum of the individual stock exposures. So the weight on stock A times 1.2 plus the weight in stock B times 0.8 will give us the overall portfolio's exposure to the market factor. We want that to equal 1, and the portfolio's overall value exposure is similarly going to be the weight on stock A times 0.3 plus the weight on stock B times 0.9, and we want that to equal 0.5. So here we have two equations, both of which involve the same two unknowns, the weights in each of our assets. That structure is what we mean by a system of linear equations. A system of linear equations is a collection of equations where the unknowns appear only as themselves, multiplied by constants and added together. No squares of unknowns, no products, no one unknown with another, no exponentials. Just the unknowns themselves, each scaled by some coefficient. So why is matrix algebra useful for analyzing tools like this? Let's look at the coefficients in our two equations. They sit in a regular grid, 1.2 and 0.8 in the first equation, and 0.3 and 0.9 in the second. We can pull those four coefficients out and stack them into a 2 by 2 matrix, which we'll call matrix capital A. The first row of A is the coefficients from the market exposure equation, 1.2 and 0.8. The second row of A is the coefficients from the value exposure equation, 0.3 and 0.9. So now we've used a matrix to organize our coefficients based on which formula they belong to and based on which asset they're going to be related to. Now, effectively what we've done is just remove the weights from the equations. So what we need to do now is have a separate vector that ends up holding those weights. Those weights, in some sense, are the unknowns of the equation, and they're going to form a column vector, a 2 by 1, with the first entry being the weight sub A and the second entry being the weight sub B. We'll call that vector lowercase x. The right-hand side targets also form a column vector. They're what we're trying to achieve with our portfolio. It's going to also be a 2 by 1, with the first entry being our beta, which is 1, and the second entry being our value exposure, which is 0.5. We're going to call that vector lowercase b. With these three objects defined, the entire two-equation system can be written as AX equals B. It is one statement that contains both equations, and the matrix A holds all the coefficients, the vector x holds all the unknowns, and the vector b holds all the targets for our portfolio. Now you'll note that the multiplication of a matrix and a vector is something that we haven't formally covered yet, and the actual mechanics of how AX produces a column of two outputs is coming in the next few videos. But for now, the important thing is that AX equals B is just a way to package this system of equations. We have two equations written as one statement with no information actually being lost. There is one more way to package this same system. Take the matrix A and stick the vector B on the right side as an extra column. Instead of a 2 by 2 matrix, you now have a 2 by 3 table. The first two columns are the coefficients from A, and the last column is the targets from B. There's a vertical bar that people typically draw between the A part and the B part, just to remind us where the boundary is. This object is called the augmented matrix of the system, and we write it as A vertical bar B in square brackets. The augmented matrix is what we are going to actually operate on in the next few videos when we solve systems of linear equations. It carries all the same information as AX equals B, and it just lays everything out on the table in a way that's easier to manipulate. So that's the basic packaging. The system of equations is a collection of linear constraints in the unknowns. The matrix form AX equals B is a compact statement of the same system. The augmented matrix puts everything into a single table. Before we move on, there is one important question worth previewing. When we have a system AX equals B, how many solutions does it actually have? It turns out there's exactly 3 possibilities, and this is true regardless of the size of the system or the specific numbers involved. The first possibility is that the system has exactly one solution. There is one and only one assignment of values to the unknowns that satisfies every single equation simultaneously. In our 2-stock example, that would mean that there is exactly one combination of weights on stock A and stock B that hits both factor targets at the same time. The second possibility is that the system has an infinite number of solutions. There are many different assignments of values that satisfy every single equation. This shows up when there is some redundancy in the equations, or when there are more unknowns than effective constraints. In a portfolio context, that would mean there are many different weight combinations that all hit the same factor targets. The third possibility is that the system has no solution at all. There is no assignment of values that satisfies every single equation simultaneously. And this shows up when the equations contradict each other or when there are more constraints than the unknowns can actually satisfy. In a portfolio context, that would mean the targets you set cannot be achieved by any weighting of the available stocks. 3 cases: unique solution, infinite solution, or no solutions. Which case you end up in depends on the structure of A and the relationship between A and B. We'll work through how to tell which case we're in and how exactly to solve the unique solution case in the next couple videos. Ruth puts down her typewriter. The methodology in her dissertation involves constrained portfolio problems all over the place. Every one of those problems is going to be written in the same form, AX equals B, and every solution she works out is going to be solved by manipulating the augmented matrix. The augmented matrix is the workspace that the rest of this module is going to operate on. So that is what a system of linear equations is, and how matrices package it. The system itself is a collection of equations where the unknowns appear only as themselves, scaled and summed. The matrix form AX equals B expresses a whole system as one statement, with A holding the coefficients, X holding the unknowns, and B holding the targets. The augmented matrix, A vertical bar B, puts everything into a single table that we are going to actually operate on. And every system has one of those 3 outcomes: a unique solution, infinite solutions, or no solution at all. Which one we end up in depends on the structure of A and how it relates to B.